Electronic devices, junction diodes, part 2, series on semiconductor devices and circuits, lecture number 2.12. Diodes, junction diodes are unilateral devices. They exhibit rectifying properties. It implies they allow the flow of current in one direction, but they prevent the flow in the opposite direction. Hence, one can say current in the diode depends upon the way the voltage is applied across its terminals. In the present session, the focus is on mainly current, the relation between current that is flowing through the diode and the voltage that is applied across its terminals. There is an equation. This equation is known as Diode equation or Shockley diode equation. This equation describes more or less completely regarding voltage current relation pertaining to PN junction diodes. In this session, we consider this particular relation, and along with it, we also discuss about temperature dependence of current through the diode. Current in the diode changes with temperature. This aspect can be understood very easily since all semiconductors change their behavior with the change in temperature. Apart from these two aspects, some more interesting aspects are also considered in the present session. With this small introduction, now let us move to the core session. Let us begin with by mentioning a few points regarding biasing. A diode which is biased is called as a biased diode. Then we need to define what is bias. What is biasing? Applying a DC voltage across the diode is called biasing. When anode is at higher potential, it is called forward bias. And if cathode is at higher potential, it is called reverse bias. When we say anode is at a higher potential, it implies it is at a higher potential when compared to cathode. When we say cathode is at higher potential, it means cathode is at higher potential with respect to anode. So anode is at higher potential, then the diode is said to be forward biased. If cathode is at a higher potential, then it is called reverse biased. Under forward bias, resistance of the diode is small, current is large. The process involved in the flow of current is diffusion. Under reverse bias, resistance is large, diode's resistance is large, consequently current becomes small, and the phenomena that is associated with the current flow is drift. We know in semiconductors there are two phenomena which can cause current flow. One is drift, another is diffusion. Diffusion results whenever there exists a concentration gradient of the charge or current carriers. Drift exists, comes into being wherever there is a potential gradient or field. Here important point to be kept in mind is when diode is forward biased, it exhibits small resistance. As a consequence, current through the diode becomes large. The process associated with this current is diffusion. When bias is reversed, diode exhibits huge amount of resistance. Naturally, current that flows through the diode becomes small. The phenomena that is associated with this current is drift. In both P and N regions, carrier concentration is high, making their conductivity extremely high. Consequently, field in these regions non-existent, negligible. So what he is trying to tell is, consider diode P region on left side, N region on the right side. Carrier concentration on P side or N side, it is approximately equal to impurity concentration. Impurity concentration is usually 10 power 12 or 13 atoms per cm cube. This 10 power 13 is a huge number. Because of this largeness, conductivity of P region and conductivity of N region, it becomes very large. When conductivity is large, field becomes non-existent, because if we consider Ohm's law, point form Ohm's law, J equal to conductivity multiplied by E. From this we can see field is equal to J by sigma. When sigma becomes huge, E becomes very small, negligibly small. So it results in this statement. Because of high conductivity, the resistance of P and N regions naturally is low. Conductivity is very high. Resistance naturally becomes low or negligible. Hence, voltage applied across the diode appears directly across the depletion region. Here what he says is, as this conductivity of P region, conductivity of N region is very high, resistance becomes very small, negligible. So when we apply certain voltage, maybe positively biasing or it may be negatively biasing, it doesn't matter. Whatever voltage we apply, it directly goes and sits across, it appears directly across the junction region. Total voltage, complete voltage, whatever we applied, whatever we connected across the diode appears across the junction. Of course, this statement is only approximately true, because however large the conductivity of P and N regions may be, it is not infinity. Therefore, resistances of P and N regions cannot be zero. Of course, it is near to zero, very small, but not zero. Naturally, certain amount of applied voltage. It may be small. It appears across P region, certain amount of voltage. It is also very small, appears across N region, remaining only appears across the junction. That is the reality. Some more points regarding biasing of the diode voltage. The voltage across the DR stands for depletion region, is V0. V0 minus V, V0 plus V. Three values are given. V0 when the diode is not at all biased. That is when the diode is under OC, open circuited condition. V0 minus V when it is forward biased. It is V0 plus V when the diode is reverse biased. In these expressions, V0 is a constant pertaining to the diode. It is called built-in potential. When diode is formed by adding impurities, p-type impurities on one side and type impurities on the other side, junction region in between these two regions come into being. Across this junction region, there comes into being a certain amount of potential. That potential is called built-in potential. The built-in potential is something that has come into being on its own, whereas V is bias voltage. This voltage is one that is applied by us, connected by us across the diode. This is V. This is V0. So this point tells something about voltage that exists across the junction. Width of the junction region. DR width. DR, as already mentioned, stands for depletion region. This width is non-zero on OC, becomes large under reverse biased condition, decreases to small when the diode is under forward bias. So width of the junction region varies with the applied voltage. Voltage across the depletion region varies with the applied voltage, type of bias. In the same way, width of the junction region or depletion region also varies with voltage and type of bias. Width depends upon applied voltage. With increase in RB voltage, the width of DR increases, and with the increase in forward bias voltage, the width of DR decreases. The penetration depth into a particular side of the junction is inversely proportional to impurity concentration. So this point has certain special importance. What it says is, this is P region of the diode, this is N region of the diode, this is, let us say, interface. Surrounding the interface, there exists junction region. The width of junction region on P side, this part, it is usually indicated by WP. You can call it WA also. This WP, it is dependent upon impurity concentration on P side. Similarly, WN or WD. This WN depends upon impurity concentration on N side. It can be shown that this particular widths, they are inversely proportional to impurity concentrations. A few points regarding built-in potential. Under OC condition, there exists a potential across the PN junction, and this potential is called built-in potential. It is, as already mentioned, it is indicated by V0. Its value of V0 depends upon the type of junction as well as the doping concentrations on both sides of the junction. So type of junction, it means the value V0 depends upon whether the junction is a step graded junction or linear graded one. Type refers to step graded or linear graded, and V0 also depends upon the doping concentrations on both sides of the junction. For step graded junction, V0 can be found equal to Vt. Vt stands for volt equivalent of temperature. Its value is equal to 26 millivolts at room temperature. It can be shown it is equal to T by 11,600, temperature by 11,600, 26 millivolts. So Vt multiplied by natural logarithm Na/Nd. Impurity concentration on P side is Na, Nd is impurity concentration on N side, divided by Ni square. Ni stands for intrinsic carrier concentration. This expression can be shown equal to Vt natural logarithm Pp0 by Pn0 equal to Vt natural logarithm Nn0 by Np0. Pp0 means whole concentration on P side under equilibrium conditions. Pn0 means whole concentration on N side under equilibrium condition. Similarly, Nn0, it stands for electron concentration on N side under equilibrium conditions. Np0 means electron concentration on P side under equilibrium conditions. In this slide, you can find a small table, two-column table. In one column, doping density is given, 10 power 14, 10 power 15, 16, 17, 18, 19. In the next column, the value of contact difference of potential. Built-in potential is also known as contact difference of potential. So values, built-in potential values for different doping concentrations is given. For 10 power 14 it is 0.7. For 10 power 19 it is 1 volt. So it is less than 1 volt. Its range is roughly 0.7 to 1 volt. Now we move to the heart of the present session, that is Shockley diode equation. What is this equation? It gives the connection, the relation between the current that flows through the diode and the voltage that is connected across the diode. So it is basically current voltage relation of a diode. It is given by I. I means current through the diode, terminal current strictly speaking in amperes. It is equal to I0. I0 is a constant. It is called reverse saturation current multiplied by e power V by eta Vt minus 1. V means applied voltage. Eta is a constant. It is called emissivity. Vt, as already mentioned, it is volt equivalent of temperature, 26 millivolts at room temperature. I0, which is also a constant, it is called a reverse saturation current. This I0 is given by this formula. A means cross-sectional area of the diode. E means charge over an electron or hole. dP means diffusion constant pertaining to holes. Lp means diffusion length pertaining to holes. Pn0 means hole concentration on N side under equilibrium condition. Similarly, Dn, diffusion constant pertaining to electrons. Ln, it is diffusion length pertaining to electrons. Np naught means electron concentration on p side under equilibrium condition. This expression can be shown equal to A into E multiplied by dP by LP Nd. dP LP we know, Nd also we know, it is impurity concentration on n side, plus dN by Ln multiplied by Na. Na stands for impurity concentration on p side multiplied by Ni square. Ni is intrinsic carrier concentration. It depends upon temperature. It also depends upon the semiconductor. Now, we spend some time on this equation. It is so important an equation that we need to know each and every aspect of this equation, because we come across this equation so frequently. Now, consider a diode lying along x-axis with the junction at x equal to 0 with the n side on positive axis. Assume the junction width is negligibly small and recombination and generation in this region is nil. Now the total diode current I is sum of minority carrier currents at the junction. Here what we are going to do is we try to understand how Shockley diode equation has come from the basics of semiconductors. For that, consider diode, P region, N region. Let us suppose it is lying along x-axis with N region falling over positive axis, P region on negative side. Now, what he says is the total diode current I is sum of minority carrier currents at the junction. The current inside the diode, it can be split into two parts. One part is called majority carrier current. Another part is called minority carrier current. Total current is the sum of these two currents. This is one aspect we have to keep in mind. Second aspect that should be remembered is majority carrier current after entering into the other side, it becomes minority carrier current. Minority carrier current on the other side becomes majority carrier current. If we consider a point just on the edge of junction region here, total current is majority carrier current on P side plus minority carrier current on P side. In the same way, one can say total current is majority carrier current on N side plus minority carrier current on the N side. Of course, these two relations, they hold good all along the length of P region, all along the length of N region. But consider a point just over the edge of junction. Here, at this point, one can say majority carrier current on P side plus minority carrier current on P side is equal to total current. But majority carrier current on P side, after crossing the junction, it becomes minority carrier current on N side. Therefore, one can say total current at the junction is P side majority carrier current, which is of course minority carrier current on N side at the junction, plus minority carrier current on P side. As we are not considering, we are assuming recombination and generation in this region is nil, majority carrier current on P side, minority carrier current on N side across the junction becomes same. They don't change. Same argument can be put forth regarding majority carrier current, minority carrier current on the N side too. Conclusion is this: current I is sum of minority carrier currents at the junction. Now, with this understanding, let us move further. I means total current. Current, let us say, that is entering P region, or current that is leaving N region. This I is equal to IPN. I stands for current in amperes. On P side, IPN stands for I for current in amperes, P due to holes, N on N side. So this is minority carrier current. 0, it indicates that we are considering at the junction, plus INP. I stands for current in amperes due to electrons on P side. So it is minority carrier current. 0 means at the junction at x equal to 0. So total current is minority carrier current on N side plus minority carrier current on P side. Now IPNX. I stands for, as already mentioned, current in amperes. P due to holes on N side at X. At X means somewhere here, not at the junction. Here, somewhere here, at a distance of X from X equal to 0. It is equal to A JPN of X. A is cross-sectional area. J stands for current density, amperes per meter square. This is equal to minus A E dP dPn of x by dx. One can identify this relation as the one that gives diffusion current. It is related to diffusion current because this relation, the reason for its relevance here is that minority carrier current is mainly due to diffusion, right? Now Pn of x, Pn of x means hole concentration on N side at a distance of x. It is equal to Pn prime of x plus Pn naught. Pn naught means hole concentration on N side under equilibrium conditions. Pn prime of x means it is injected carrier concentration, hole concentration at a distance of x on N side. Now let us move further. Pn prime of x can be expressed as Pn prime of 0 e power minus x by Lp plus Pn naught. Now IPN of x, we are here, IPN of x is minus AE dP d Pn prime of x by dx, which becomes equal to minus AE dP d by dx of Pn prime of 0 e power minus x by Lp. Differentiation and a little bit of manipulation gives us IPN of x as AE dP by Lp multiplied by Pn of x minus Pn naught. Now, from this expression, IPN of 0, it can be seen as AE dP by Lp, Pn of 0 minus Pn naught. But Pn of 0, it is equal to Pn naught e power V by Vt. This relation is called law of junction. It gives hole concentration on n side at the junction from equilibrium hole concentration on n side for a given applied voltage V. Now, using this particular equation, which is called a law of junction, one can write IPN of 0 equal to AE dP by LP. Pn naught e power V by Vt minus Pn naught. It turns out to be equal to AE dP Pn naught by Lp into e power V by Vt minus 1. In the same way, one can write relation for INP of 0. INP of 0 means current in amperes due to electrons on p side, minority carrier current on p side at the junction equal to AE dN NP naught by Ln e power V by Vt minus 1. Total current is, of course, IPN of 0 plus INP of 0. Combining these two expressions, this one and this one, we will be getting a constant. This constant is named as I naught e power V by Vt minus 1. This is the way this current voltage relation of a PN junction diode is derived. Graphically, one can sketch voltage current characteristic of a diode. In A is shown ideal diode characteristic. Notice, ideal diode is one which exhibits zero resistance under forward biased condition and infinite resistance under reverse biased condition. But ideal diode is an ideal diode. They do not exist in reality, in the real world. Anyway, the conceptual background of ideal diode, it is shown, illustrated in diagram A. Positive side, forward biased side, it is zero resistance, short circuit. Reverse bias side, it is OC. In B is shown current voltage characteristic of a practical diode, PN junction diode or semiconductor diode. First we consider forward biased diode, means this side, positive voltage side. One can notice as the applied voltage is increased, initially there is no current in the diode, but when the applied voltage reaches a certain point, in this case it is 0.1, the diode starts conducting. After that, with increase in voltage, current also starts increasing. The relation between voltage and current after starting the flow is exponential. This is exponential. This kind of things, exponential rise, keep on happening until the applied voltage reaches a value equal to V naught. V naught stands for built-in potential. When the applied voltage approaches V naught, what happens is the diode loses its rectifying properties. The diode loses its barrier potential and it starts conducting heavy currents, resulting in permanent damage to the diode. So this is as far as forward biased diode is concerned. Now come to reverse direction. When applied voltage is negative, we say the diode is reverse biased. One can see under reverse bias, the diode carries, it flows small amount of current. This is very small. This current is called reverse saturation current. And this current, one can see, it is independent of voltage. For all voltages, current remains the same. Notice here current is, here current, here current, here current, everywhere it is same. And this kind of things, this state of affairs continues until the applied voltage reaches certain value. This value is usually called Vz or Zener voltage. When applied voltage crosses Zener voltage, then the diode starts conducting heavily. It starts carrying huge amount of current. When current flows in huge amounts, naturally, lot of heat gets generated, resulting in a permanent damage to the diode. Before going further, one has to understand an important point. There is a range of voltage for operating a diode. Positive side, one can operate, one can work with the diode only up to a voltage equal to V0, built-in potential. In reality, the voltage is far below than V0. On reverse side also, there is a voltage. If the applied voltage is increased further, more than this voltage, above this voltage Vz, then permanent damage happens to the diode. So on one side it is V0, on the other side it is Vz. These are the limits. Some more points regarding Shockley diode equation. In the equation I, it is in amperes. It is the current through the diode, and it is positive when conventional current is from P to N region. In the equation V, it is in volts, and it is voltage across the diode, and it is positive when the positive plate of the battery is connected to anode and the negative plate of the battery is connected to cathode. Eta is a constant, as already mentioned. It is called emission quotient. Its value is unity for germanium diodes. A value of 1 indicates negligible carrier generation recombination at the junction. For silicon diode, of course, its value is 2 when applied voltage is less than 0.5. When applied voltage is more than or equal to 0.5, then it is 1. Its value of 2 accounts for carrier generation and recombination within the bulk and on the surface of the transition region in silicon diodes. I naught in the equation, its units are amperes. It is a bias independent constant known as reverse saturation current, and its typical value is 10 power minus 14 amperes. It represents the value of the current that flows in the diode under reverse biased condition. In practical diodes, however, the reverse biased current usually exceeds the magnitude of I naught, mainly due to the existence of leakage current, which is around 10 power minus 9 amperes, flowing along the surface of the diode, and current which obeys Ohm's law relationship not accounted for in the above equation. What he says is, on paper one can calculate the value of I naught. Roughly it is 10 power minus 14 amperes. But in practice, it is more than 10 power minus 14. If you go to a diode and measure the current that flows through the diode under reverse biased condition, let us say with an ammeter, then one can find that current more than 10 power minus 14 amperes. What is the reason? He says leakage current and also current which obeys Ohm's law. Some more points regarding biased diode. Under forward bias, V is positive in the equation. I is large, predominantly due to diffusion. Current direction is P to N side. You see, current is moving like this, P to N side. VI relation is exponential. I equal to I naught e power V eta Vt minus 1. And reverse bias, V is negative. I is small in the equation. V is negative in the equation. I is small. And it is predominantly due to drift. Current direction is from N to P side. In this case, I equal to minus I naught. Current is independent of voltage. Notice, under forward bias, I depends, current through the diode depends upon applied voltage. Under reverse bias, I equal to I naught. I naught is a constant. It is independent of voltage. Now, a few points regarding cut-in voltage. We have already seen when the diode is under forward bias, the current in the diode, it starts flowing only when bias voltage is more than certain value. Before that, there exists no current. Even though it is under forward bias, even though the applied voltage is more than 0, current is 0. Current starts only when applied voltage is more than certain value. That voltage is called cut-in voltage. According to diode equation, the current through the diode is non-zero when it is forward biased, even with a very small voltage. So this is diode equation. According to diode equation, current has to flow even the applied voltage is very small, nearly 0, when it is under forward biased direction. But in reality, it is not so. However, in practical diodes, the current is almost 0 until forward biased voltage is more than certain value known as cut-in, offset or breakpoint threshold. These are different names for cut-in voltage. This voltage is indicated by V gamma and its value is 0.2 volts for germanium, 0.6 volts for silicon. These are approximate values. Another term also requires to be introduced to you. This is appropriate time to introduce the term of break region. What is break region? The resistance of diode changes from very large to small value at cut-in voltage. The change is not abrupt, it occurs in the region surrounding the cut-in voltage. This region is called break region, which can be defined as the voltage range over which the diode resistance changes discontinuously from very large RR to very small value RF. So what he is trying to tell is, this is VI characteristic under forward biased condition. This is cut-in voltage. After 0, before cut-in voltage, here the resistance is infinity, very large. After cut-in, resistance starts decreasing. Okay. So around cut-in voltage, one can imagine a region where resistance decreases from high to low. That region is called break region. Reason for different cut-in voltages in germanium and silicon is mainly due to reverse saturation current in germanium diode is larger than that in silicon. This is one aspect. Second aspect is eta equal to 2. Initially, that is for smaller voltages. The dependence of current on voltage is small in silicon. Here he is giving you the reasons for different V gammas for silicon and germanium. 0.2 for germanium, 0.6 for silicon. Why high value for silicon? This is the reason. Now, some more important points regarding VI characteristic of diode or Shockley diode equation. These points are given under temperature dependence of diode characteristics. Before going to the actual points, it is better to remind us the fact that behavior of all semiconductor devices changes with temperature, and also it is considered to be the biggest drawback pertaining to semiconductor devices. Diodes we are discussing about PN junction diodes, semiconductor diodes. They also change their behavior with the temperature. This change in their behavior, in their VI characteristic, it is being explained in the present slide. Diode's behavior is dependent upon the temperature due to presence of temperature in I0 in Vt. Notice in the expression for I0, you can find temperature. For example, in the expression there is Ni square. Ni stands for intrinsic carrier concentration. Intrinsic carrier concentration is a temperature dependent constant. So I0 also depends upon temperature. Similarly, Vt is T by 11,600. T stands for temperature. So Vt, in the expression for Vt also there is temperature. So I0, Vt both depend upon temperature. Naturally, current of the diode also depends upon temperature. It is possible to quantify this dependence in terms of change in I0 and change in V, the bias voltage, both with respect to temperature. There are 2 points which take care the entire, which account for the entire temperature dependence of Shockley diode equation. First point is reverse saturation current I0 increases approximately 7% per degree centigrade for both silicon and germanium. It implies reverse saturation current doubles for every 10 degree centigrade rise in temperature. Mathematically, it can be written like this. Reverse saturation current at temperature T is equal to reverse saturation current at temperature T1 multiplied by 2 power T minus T1 by 10. Current doubles. Double means 2. Every 10 degree rise in temperature means T minus T1 by 10. Here I0 of T is reverse saturation current at a temperature T and I0 of T1 is at a temperature T1. Dependence of I0 on temperature can be understood from its basic expression containing diffusion constants and intrinsic concentration. This point is already mentioned. The second parameter that describes temperature dependence of VI characteristic is bias voltage quotient of temperature. It is given by dV by dt is equal to minus 2.5 millivolts per degree centigrade. Notice this is negative. Now we come to the end of the session. Before closing down, let us recollect the important points or aspects we touched upon in the session. From the beginning till the end, the discussion is basically on biased diode. Under forward biased condition, what is the current? Under reverse biased condition, what is the current? What are the phenomenon that dominate under forward biased condition? Is it a drift or diffusion? What is the phenomena that dominates under reverse biased condition, forward biased condition? All those things we touched in addition to the main aspect, that is Shockley diode equation and cut-in voltage and temperature dependence of VI characteristic of diodes. Hope this session is useful to you. We meet again with a new topic in another session soon.